Hey everybody, welcome to Madden Science. Today we're talking about air pollution. Hey everybody, welcome to Madden Science. We're doing air pollution. Coming to you, Unit 7 in AP Environmental Science. Let's get started. Here's where it fits in. For our flipped classroom lesson ideas, same as always. Notes, drawings, need some questions. We need some answers too. There'll be a few spots where I say, hey, in your notes, get this down, do this conversion, look up this stat. This video in particular has a lot of density, so there's going to be some figures in here where I'm going to zoom in. We may not talk about each and every specific, but that's where the pause button comes in. So you can pause, add a few notes that maybe I don't say out loud at any particular point. In the end, you need to add one comment. So some of these I may ask, like, hey, is it better air pollution wise for me to drive with my windows up or my windows down? How about exercise? Does it matter if I'm exercising in maybe a highly polluted area or if it's a higher ozone day? Is that going to have a bigger impact on my respiratory health? So is it good to be biking but bad to be biking in high ozone? Things like that we want to figure out as we go. All right, Unit 7, fitting between energy and land and water pollution. Here it is in detail. What we're going to cover for now. We're going to just do a little intro. We're going to jump in, kind of combine 7.1 and 7.4. We'll also talk about indoor air pollutants and jump down to noise pollution. So we got a little bit of air pollution, a little bit of noise pollution. Here are the units broken down like this along with our chapters and big ideas. You see big idea right here. These are all going to be within sustainability. So that's going to kick us down to big idea number 4. We've got our learning objectives shown here. So these are our objectives or targets. For 7.1, looking at combustion, the materials that are released during combustion and, from either a power plant or fossil fuel burning, how that affects air quality, what's going on with the Air Quality Act or Clean Air Act and Environmental Protection Agency. Jump in down. 7.4 again, talking about particulate matter and CO2. We're going to throw that mostly into 7.1 or combine the two. These other parts we'll talk a little bit about in class. Here in the video we'll also address indoor air pollution, which is where I'm at now. Perhaps 2-5 times as bad as outdoor pollution. We'll talk about why that is. We'll talk about decreasing and acid rain or acid deposition coming up, and then we'll end with noise pollution. So here are the sections and the vocab words. See 7.1's got a whole lot of vocab. In a sense, you could almost cover the whole unit just here. So intro will lean heavily on this particular section. 7.2, again, photochemical smog, thermal inversion. 7.4 will lump together. Indoor, also a lot of terms. 7.6, reduction, acid rain, and then noise. Here's a diagram from Biozone. It's got pollution and global change. So this actually takes us through the end of the year in a sense. It's got us in Unit 7 with air pollution, covering land and water also, and then talking about global change in the end. So you can kind of see in here broken down into quadrants, types of pollution, what those impacts will be. I'll mention it a few times. We'll just touch on some of the human health related issues related to noise and air pollution, also a little bit on light pollution, but we'll probably do a separate video as the health concerns relate not just to air, but also to land and water. So we'll fit that all together in a separate video. Again, we got climate change and then conserving biodiversity. All right, in terms of videos and resources, we've got, if we skip all the way over, so jump over to Madden Science, we got AP Environmental Science, all my playlists, which will kick us over to YouTube. And for Unit 7, you can see the videos that have been added here. If you got a number of other cool ones, you think they should be part of it, certainly put a comment in the description. I'll try and add that to this list. All right, Jumping back on this one. So that's some of the videos we've got there. In 7.1, the same slide we already saw. From Biozone, they're giving us some causes of pollution. We got the industrial piece, which is probably the one we think about most, tied in with what we do with transportation, our motor vehicles. You see a little bit of the chemistry. What are the compounds that are released here, primarily by industry, and also those by your car or taking a plane or your boat or your van or your bus. There's also an important piece that people don't always think about, the natural side, right? There are plenty of natural components and causes of air pollution. In this case, they're showing volcanoes and forest fires. So recently, forest fires playing a big role in global ecosystem. This is just saying that, well, in fact, climate change is exacerbating some of these changes. Here's a slide just from our fairly recent brush fires in Australia. Here you can see some air quality indexes and the changes throughout the month as they skyrocketed in December and January. You can also see big changes with volcanoes, and then even things like dust storms that have a big impact. So here you have dust flowing off of the Sahara into the Atlantic, helping to actually seed much of the biodiversity in the ocean. So on the bottom of the food chain with plankton and phytoplankton. So here's an interesting article about Saharan dust feeding ocean plankton. Get an image of air quality index. Where we're living, thankfully, it's almost always below 100. Hardly ever even on record above 100 in Florida. You can see a lot of influence, not just on what kind of fossil fuels are being burned, population density, but how close are you to water or places where people don't live? What are the weather and wind patterns? What kind of geological formations are, including mountains? So hence differences on east and west coast. If we kick over to here, you can look at air quality indexes on the internet. And these are pretty striking. So that'll take a second to refresh. The other day, so we are over here. If we zoom in, you can see where we're at. Coming in currently right around 23. If we zoom back out, just give me a hard time here, and we pull over. The other day in class, we had in parts of New Delhi topping out at 999. Now, I'm not sure if that's where the scale stops, but you can see today way lower and yet still pretty significant. And if you look at the colors here, you're going from good to moderate, unhealthy, very unhealthy, and then hazardous. So big deal on those guys. You can see again lots of different harmful health impacts. You can see some from particulate matter, what's going on with fine particles. Obviously, it's primarily going to be with respiratory system, but it goes far beyond that. Just in terms of vocab, primary pollutants are going to be the ones that are released from a source. Secondary will be when primary pollutants react with each other and components of the ecosystem, say sunlight or UV. This also shows differences in resident time. So how long are those pollutants going to be hanging out in the atmosphere? Short time, well, those pollutants are going to stay around locally. They stay a long time. If the resident time extends longer, again, hours, days, weeks, months, years, centuries, then those guys are going to have much more of a global impact. And you can see the differences in those molecules. This is going to show you what the Clean Air Act started to designate for the EPA to monitor. 6 different pollutants. You can see their presence in the atmosphere. Carbon monoxide, VOCs or volatile organic compounds, nitrogen oxides or NOx, sulfur dioxide or even sulfur oxides, particulate matter, and lead. Now we'll talk in depth about one other one in addition to this, which is ozone. But these are the ones outlined initially 1970 Clean Air Act. You can see what they are. Name, symbol, molecule, where they're coming from, and problems that are caused. Keep in mind, way back to the beginning of the year with biochemistry and the impact of chemistry on our environment. So if we zoom in just with ozone, it's O3, quite a bit different here at ground level or in the troposphere than it is up in the higher elevations, or altitudes I should say. So has a protective anti-UV properties high up in the stratosphere. Here at the troposphere it's highly dangerous. So source would be combustion, VOCs, and NOxes that combine, and then breathing problems for people with lung disease, asthma, kids, older adults. Particulate matter, abbreviated PM, usually designated by its size, measured in microns. So if you see in here, right, that's our size, and it's in micrometers, or meters times 10 to the negative 6, or a millionth of a meter. So pretty small. You can even get down to 1 or 1 micron. So again, coarse versus fine or ultra fine. Obviously these can be damaging when inhaled. If we skip next to nitrogen dioxide or Nox gases, the X would mean you could have NO, NO2, NO3. Primarily from combustion, vehicles, power plants. Asthma is worse, contributes to ground level ozone and acid rain. Carbon monoxide, not to be confused with carbon dioxide, so it's one oxygen along with one carbon, so CO as opposed to CO2. Incomplete combustion in vehicles. Some of it's let off by power plants through fossil fuel burning. Both vehicles and power plants are going to have catalytic converters that want to help decrease the amount of CO that's released. Low levels harmful to people with heart conditions. High levels it could kill you. This is what happens in some cases when people asphyxiate. SOxes or sulfur dioxides, SO2, burning coal, oil that contains sulfur. So we went to our field trip to a natural gas burning power plant, and they had almost zero sulfur dioxide release. They had plenty of nitrogen dioxide. And some of the SO2 would be when they go on backup, say, for burning diesel fuel. So breathing problems also contributes to acid rain. Lead, not nearly as big of a deal these days as it had been, seeing as it's no longer part of the gasoline that cars burn. So historically, would be in cars and vehicles. This is another awesome infographic, shows a lot of detail. This is from our friends over at compoundchem.com. A lot of good resources there, similar to what we just saw. So carbon monoxide, carbon dioxide, certainly the biggest threat is with global climate change. Nitrogen oxides. Again, earlier I mentioned about pausing. So if we want to get down a little bit more of what's in here, it takes you more time than what I'm saying, then go ahead and give it a pause. We got ammonia, hadn't been mentioned before. We skip back over volatile organic compounds. Important to note that these guys are emitted naturally by vegetation. Can contribute to smog. Ozone, again, protective for UV radiation, but at ground level, quite a harmful pollutant. Persistent organic compounds, particulate matter, and then heavy metals. All right, some good news. Here in the United States, you can see from both of these tables, you got a steady decline in the amount of pollution in our air. So for all of these indicators have gone way down by 72, down by 99%. And this was in 2014, so it's even gotten further. Now, this is all happening even with an increase in emissions. So people are burning more fossil fuel, they're driving their cars more, and there's a greater population. And yet, these indicators have decreased quite significantly. What's cool about this unit is it's got a lot of data, a lot of datability. This is from a purple air monitor. Here's what we've got at school with our weather stem. Again, you can zoom in on here, see particulate matter, see thermometer, obviously, wind chill, barometric pressure. Here's a little bit of data we collected. So we did with our app on our phone, Decibel X, to collect noise pollution levels. We also use our Pocket Lab Airs, and you can see that these are the averages of kids, and we looked at particulate matter, air quality index, carbon dioxide, and ozone. And then for sound, we just looked at decibel level. We averaged them out and looked for trends and interesting findings. Here's our long term. So we did a time lapse to see a lab where we made some ozone paper, and it turned out pretty cool. So here it is after the fact. So if you keep it in a Ziploc bag, it doesn't have any ozone in there, so it remains unreactive. Here they are after sitting outside for 8 hours. You can then look at this and compare over time. As long as you know the relative humidity, you can see what generally the ozone level was for that day and location. Here's a closer up view. So here's what I'm going to do. If I take this, it faded a little bit, but we had it pretty close to a 9 right here. So I'm going to go ahead and scale it at a 9. And then this happened to be on the 11th. So if I go up and I interpolate this data, and we go all the way across, we're at about an 85, 86 right here. So if we jump back over, what does that mean? So our Scheuben number was a 9, and our relative humidity was at 85. So we'll round to 90. So I'm going to go ahead with this right here. So if we go up from there, so 9 intercepts the 90, we go across, that's going to get us pretty much at 40 parts per billion. All right, so let's write that down, and then let's convert it. So if we got 40 parts per billion, how many parts per million is that? Now I'm running another one of these to see what would happen. We got a day that had much lower relative humidity. So what that would do would shift, which one of these lines we're going to be looking at. So these guys here. And therefore, our Scheuben number will probably be a little bit lower. Anyway, we want to see what that turns out. I'll get back to you when that time lapse is finished. We also did a cool lab in class with particulate matter, collecting indoor and outdoor. One lesson learned from this is get the thinnest, most even, smoothest coat of Vaseline or petroleum jelly on there. All right, another cool thing about this unit, lots of research. So not just on the law aspect of it or the historical changes that are taking place, the health implications, the biochemistry, connections to ecology, it's all over. We got into news. We talked about in class even connections of air pollution to our very DNA. This article written by Carl Zimmer, really fascinating. All right, and then we had our trip to the power plant, which was really fascinating. We had awesome people working with us. This is burning natural gas. Most of the carbon monoxide that's produced is going to be converted to carbon dioxide in their catalytic converters here in this stack. You can see historically that there's been a greater increase in natural gas, a shift slightly away from coal. You can see that ends up being a little bit cleaner in terms of less energy produced, or consumed rather, and lower CO2 emissions. Here's a diagram that shows the comparison. You can zoom in on that. One of the bigger emitters of some of our air pollutants is our vehicles, the cars that we drive. Some of the things that are going to be coming out of here are going to be carbon monoxide, certainly some carbon dioxide, nitrogen oxides, sulfur oxides, and particulate matter. Just a quick refresher on the distinction between carbon dioxide and carbon monoxide. Carbon monoxide can be deadly in the short term. It also can outcompete oxygen in binding with hemoglobin. So hence the asphyxiation that can take place and death. Oops, skipped over one of these. All right, so sources of transportation air pollution. We got the road ones and non-road. Again, we're most likely to be contributing right here with light-duty vehicles. Here are some ideas for solutions, which would be great. Obviously, catalytic converters, changes in fuel standards, engine technologies that have shifted. Again, if car companies want to do it, they can do it. Transmission technologies, different filters, alternative vehicle technologies, obviously electrical, plug-in hybrid options there. You might recall from a few years ago the problems with Volkswagen lying about their emissions. Here you can see some of the polluting compounds, and then some solutions in cars, catalytic converters, catalytic reduction, and Nox absorbers. All right, quick view. Again, we will talk more in depth about some of the deadly impacts of air pollution coming up soon, I promise. Here's another one that shows some health impacts, so we'll come back to those. All right, so particulate matter. Broken down most commonly PM10 and PM2.5. You can go even finer than that. We'll get to the scale in a minute. So what's making up particulate matter? Note from before, it didn't have any particular chemical formula because there's lots of different options. Here you can see all the different things that would compose particulate matter depending on where you are. Potassium, sodium, calcium, aluminum, silicon. So tons of different pieces of the periodic table, from coal burning, oil burning, biomass, diesel, burning refuse, sulfates, nitrates, primary, secondary, so pretty complex in there. Here you can see around the world a little bit blurry, but if we zoom in over here, it's showing you sources. Where are the particulate matter, or where is the particulate matter coming from? Traffic, industry, domestic fuel burning, we're coming back to that in a few minutes. Natural sources like soil dust, which we saw in the Sahara, or sea salt, and then unspecified. So that's pretty interesting. Shows you also particulate size and like what is it. Note too that there's a biological piece in it. So there's living organisms that count as particulate matter. More on that with indoor air pollution. We got one of my favorite apps, the Scale of the Universe. So let's check them out real quick to see where we're at. All right, it's restarting real quick. So if we zoom in here, we got different size, right? So a glass marble coming in at 1.5 times 10 to the negative 2 meters. So zooming in just to give you an idea where we're at with particulate matter. So this grain of sand is coming in at 500 micrometers or microns. Again, particulate matter is like 10 and below generally. So a 10 and below is going to give us, a silt particle, 50 microns. We got to scoot in a little bit closer. White blood cell, 10 microns. Okay, so that's about the neighborhood we're in, kicking it down to, say, E. coli at 2 microns. So that's kind of our range. 10 down to, truthfully, much smaller than 2.5. And then you could zoom, in and way out. Anyway, ton of fun. Thanks, Scale of the Universe, folks, for your work. This also gives you an idea just in terms of sand. So remember back to our unit on soil, the human hair in this case, particulate matter shown here. We've got nitrogen oxide emissions. Here's another cool one with one of my favorite websites, Windy. So we kick over here and we jump on Tallahassee. Last thing I was on was carbon monoxide. So currently we're at 159 parts per billion carbon monoxide concentration. You could kick that over and look at sulfur dioxides or Nox gases. Here's some volatile organic compounds in Paterson, New Jersey, kind of near where I grew up. Here's a list of things that would count as volatile organic compounds. In terms of sulfur dioxide, interestingly, recently India overtook China. And if you look at the stats here, China reduced by 75%, whereas India kicked up 50%. And a map of that would look like this. And then recently, or more recently, we got a change in the Wuhan region based on sulfur dioxides and burning of organic matter. All right, let's wrap up this part with ozone. So you can see that lots of different sources, both human contributed and natural, and it's really the Nox gases and volatile organic compounds with sunlight, with UV, that bust that open. Here's that production on probably a simplified scale to show. Here's some of the health outcomes, which can be pretty nasty. Again, this would be something that you could look up. Kicking back, here was our setup to try and figure out how it is that we can measure, somewhat roughly, ozone levels in our area. And we had that paper where we took potassium iodide, and that will combine with ozone, O3, to produce potassium hydroxide, oxygen, and iodine, and that iodine plus some cornstarch turns it purple or blue. And then our final note, it's a good one. The trajectory of air pollutants in the United States is going down. This is really good news. You can see from 1980 to 2015, a decrease in all of these. All right, next video, part B of this, is going to cover indoor and noise pollution. Remember, if you can, put your comments below. If you want to use this part to do your kind of research connection, go ahead and put that in the bottom too. Make sure that you include a timestamp. So where does it apply to this video? Thanks everybody. We'll see you soon.